In the 21st century, microchips are the unseen force driving our technological world. These tiny silicon wonders are the brains inside our smartphones, computers, cars, and countless other devices. They process information, control functions, and connect us to a global network. Without microchips, our modern lives would grind to a halt. The demand for smaller, faster, and more powerful chips is ever increasing. This demand fuels innovation in the semiconductor industry, pushing the boundaries of what's possible. Understanding how these miniature marbles are made from simple sand is a journey into the heart of modern technology. The story of the microchip begins in 1958 with Jack Kilby's groundbreaking invention at Texas Instruments. His first integrated circuit, a crude assembly of transistors on a germanium chip, paved the way for a technological revolution. Early chips were simple, but they demonstrated the potential of integrating multiple electronic components onto a single substrate. Over the decades, driven by Moore's law, the observation that the number of transistors on a chip doubles approximately every 2 years. Microchips became exponentially more powerful while shrinking in size. Today's advanced chips contain billions, even trillions of transistors, each smaller than a virus. The journey from sand to sophisticated microchip is a testament to human ingenuity. It all starts with quartz sand, or silicon dioxide, one of the most abundant materials on Earth. This sand undergoes a series of transformations to become the ultra-pure silicon used in chip manufacturing. The first step involves heating the sand to extremely high temperatures over 1700 degrees Celsius in a furnace. This process removes impurities and creates metallurgical-grade silicon. However, even this purified silicon is not pure enough for microchip fabrication. Further refining is needed to achieve the exceptional purity required. The purified silicon is then melted and carefully cooled in a process called Czochralski growth. This process creates a single cylindrical crystal of silicon known as an ingot. The ingot, often weighing hundreds of pounds, has an incredibly ordered atomic structure, essential for creating flawless microchips. Next, the ingot is sliced into thin, round wafers using specialized diamond saws. These wafers, typically a few hundred millimeters in diameter and less than a millimeter thick, form the foundation upon which microchips are built. Each wafer can hold hundreds or even thousands of individual chips depending on their size. The purity and perfection of the silicon wafer are paramount. Any imperfection, even at the atomic level, can disrupt the intricate circuitry of a microchip, rendering it useless. That's why manufacturers go to extraordinary lengths to ensure the wafers are as flawless as possible. After slicing, the wafers undergo a series of polishing and cleaning steps to remove any surface imperfections and contaminants. The final product is a highly polished, ultra-pure silicon wafer ready for the next stage of microchip fabrication. Section 6. Photolithography, painting with light. This is where the magic of microchip manufacturing truly begins. The real magic of microchip manufacturing happens during photolithography. This process is the heart of creating the tiny, intricate circuits that power our modern devices. This process is akin to creating an incredibly detailed photograph on the surface of the silicon wafer, capturing the essence of the circuit design with precision. But instead of using light to develop an image, photolithography uses light to etch away parts of the silicon wafer, revealing the intricate circuitry beneath. It's a delicate dance of light and material, where each step must be executed with exact precision to ensure the circuits function correctly. During photolithography, the wafer is first coated with a light-sensitive material called a photoresist. This material is crucial as it reacts to light exposure. A mask containing the desired circuit pattern is then meticulously aligned and placed over the wafer. This mask acts like a stencil, guiding the light to form the circuit design. Ultraviolet light is then shone through the mask, illuminating the wafer beneath. The UV light is a key player in this process as it activates the photoresist. The photoresist exposed to the UV light undergoes a chemical change, marking the areas where the circuit pattern will be etched. The exposed photoresist is then chemically removed, a process that reveals the underlying silicon in the desired pattern. This leaves behind the intricate circuit pattern on the wafer surface, a testament to the precision and complexity of photolithography. The wafer is now ready for the next steps in the manufacturing process, each one building upon the last to create the final microchip. Section 7. Building up the chip transistors, layers and lasers. In this section, we delve into the intricate processes that transform a simple silicon wafer into a powerful microchip, the heart of modern electronics. With the circuit pattern meticulously etched onto the wafer, the next step is to create the transistors, the fundamental building blocks of microchips. These tiny switches control the flow of electrical signals, enabling the chip to perform complex computations. This is done through a process called doping, where specific impurities are introduced into designated areas of the silicon wafer to alter its electrical properties. By carefully controlling the type and concentration of these impurities, manufacturers can precisely control the behavior of the transistors. Multiple layers of materials, including insulators and conductors, are deposited and etched onto the wafer, building up the three-dimensional structure of the transistors. Each layer serves a specific function, from isolating different components to providing pathways for electrical signals. Lasers are often used to create connections between different layers, forming the complex network of circuits within the chip. These precise laser beams can cut through layers with incredible accuracy, ensuring that each connection is perfectly aligned. This process of layering and etching is repeated numerous times to create a modern microchip, with some chips having over 100 layers. Each additional layer adds to the chip's functionality and performance, allowing it to handle more tasks simultaneously and at greater speeds. The result is a marvel of engineering, a tiny yet powerful component that drives the technology we rely on every day. Section 8. A world of purity inside the microchip clean room. Microchip manufacturing takes place in specialized facilities known as clean rooms. These controlled environments are meticulously maintained to be thousands of times cleaner than a hospital operating room. Even the tiniest dust particle can ruin a microchip, so air filtration systems constantly remove contaminants. Workers in clean rooms wear special suits known as bunny suits to prevent contamination from skin cells, hair, or clothing fibers. All equipment and materials used in the clean room are also rigorously cleaned and controlled to maintain the pristine environment necessary for successful chip production. Section 9. From wafer to chip assembly, testing and packaging. This is where the magic of turning raw materials into functional microchips truly comes to life. Once the intricate fabrication process is complete, the individual chips are meticulously cut from the wafer using a precision diamond saw. This step, known as dicing, is crucial for separating the thousands of tiny chips that have been created on a single wafer. Each chip then undergoes a series of rigorous tests to ensure it functions correctly. Automated testing equipment checks for electrical performance, speed and reliability. Technicians in cleanroom suits monitor these tests closely, ensuring that only the highest quality chips move forward. Defective chips, those that fail to meet the stringent standards, are discarded. This quality control step is vital to maintain the integrity of the final product. Functional chips, those that pass all tests, proceed to the final stage packaging. During the packaging phase, each chip is carefully encased in a protective package. This package not only shields the chip from physical damage, but also provides the necessary electrical connections to the outside world, allowing the chip to communicate with other components in a device. The package also plays a critical role in heat dissipation. As chips operate, they generate heat, and effective thermal management is essential to maintain performance and longevity. Advanced packaging techniques include heat sinks and other mechanisms to ensure the chip remains cool during operation. Finally, the packaged chips are prepared for shipment. They are carefully placed in shipping containers and loaded onto delivery trucks. These chips are then transported to electronics manufacturers around the globe, ready to be assembled into the devices that power our modern lives. The journey from sand to microchip is now complete. This process is a testament to human ingenuity and the transformative power of technology. Each step, from assembly to testing to packaging, showcases the precision and dedication required to create the tiny components that drive our digital world.